Good evening. Can you hear me?
Yes, sir. Yes.
Yeah. Thanks.
Good evening,
Yes, sir.
sir.
Yeah. Good evening. So what we will do today is we'll do week 6. Okay. So week 6, week 5 we completed yesterday, and week 6 is what we will focus on. So mainly we'll look at what is the singular value decomposition. How do we derive it? So I won't go into the detailed proof because that will take us nearly 2 hours. If we want to like prove every single point, that will take us to the singular value decomposition. It's too time consuming. So I will state whatever is essential. Some of them I'll prove, some of them I won't. Okay, so examples, we look at some 3 examples. Okay, so 2 of them here are simple square matrices and one which is rectangular. So in between we will look at some of the properties of SVD, and then we look at two applications which are specific to, which are very useful in machine learning. So one is called low rank approximation and another one is called pseudo inverse. So the pseudo inverse is something you will use a lot in machine learning techniques. Those of you who are doing it along with MLF will know, but those who are not aware of this will soon see this when you go to MLT. Okay, so that is the agenda for today. Okay.
Sir, I have one doubt from the previous session. Can I ask?
What is it? What is it about?
Sir, it is a small statement that if A is a positive definite matrix, then A is invertible. Then for that you have told one statement, if D is invertible, then A is invertible. Can you explain how it is? Where
Okay.
D is...
So very quickly, so if A is positive definite, right? So A is symmetric, right? So A is positive definite means, so A is symmetric first of all. So there is a QD transpose. There is some orthogonal diagonalization that's possible, right? So this is what it means to say that A is symmetric. Now, if A is invert, so if A is positive definite, then all the eigenvalues of A are positive. So D, if you look at D, all the diagonal elements are positive. Therefore, D itself is invertible. So D, you can compute D inverse, and if you can compute D inverse, then A inverse is just QD inverse Q transpose. Right. So this is the
Okay,
statement.
sir. Got it.
Okay. So let's now start with SVD. Okay. So SVD is I'll first state SVD. Okay. So SVD is full form is singular value decomposition. Okay. So that is what is SVD. So is a way of factoring or decomposing a matrix into, I won't say smaller matrices, but into 3 different matrices. Okay, so that is the first idea. The first idea is that it's a matrix decomposition. So we have already looked at 2 of them, right? So we have already seen 2 such decompositions before. In fact, only one, right? We haven't seen 2. We have seen one such decomposition before. What is that? We have seen already
Eigen decomposition.
Yeah, so it's the eigen decomposition, right? So where recall that the eigen decomposition for diagonalizable matrices, right? This is when it exists. So for diagonalizable matrices, so matrices which can be diagonalized, you have this PDP inverse, right? So PDP inverse is the diagonalization of A. It is, you can also understand it as expressing a matrix as a product of other matrices. And the nice thing about this was that P had the eigenvectors of A and D had the corresponding eigenvalues of A, right? So we also looked at one more special version of this for symmetric matrices. So I'll only do real matrices in today's session. Okay, so for symmetric matrices, this becomes specifically A equal to QD Q transpose, right? So for some orthogonal matrix Q, okay, so where Q is orthogonal, right? Meaning what? Q transpose Q equal to Q transpose equal to I. So these are like two decompositions we have seen, or two. So you can also call this. This can also be called matrix factorization. Okay. So there are actually several of these. There is something called LU. So there is something called LU. You can for extra reading. So there is something called LU. There is something called QR. Right. So QR is something that happens when you do this Gram-Schmidt process. Okay. LU is something that happens when you do
RE
row.
for RR2. Yeah.
Yeah. So when you do row reduction, right? So when you are doing row reduction, what you are doing is actually LU decomposition. Okay. In that sequence, there is what is called eigen decomposition, and then there is something called singular value decomposition. Okay. So I'm deleting this. Hope those who are interested, you can take a look at it later. So what is the SVD? So what is the SVD? As I already said, it's a way of breaking down a matrix into different parts. So this is the main statement. Any matrix A of shape M cross N can be represented as A equal to U
Sigma.
sigma. So this I haven't. Okay, wait. I need a shortcut for this. Otherwise, I'll end up. Once again, just give me 1 minute. You have to configure one shortcut. Just have a shortcut for sigma. So this is called up sigma. Okay. So okay, U sigma V transpose. Okay. So any matrix A of shape M cross N can be represented as the product of three matrices U V sigma V transpose. So the shapes, we first look at the shapes of, or maybe even before that, where U is an orthogonal matrix of shape M cross M. Okay, I'll write this as 3 bullet points. So U is an orthogonal matrix of shape M cross M. Sigma is a diagonal like matrix. It's not exactly a diagonal matrix. It's a diagonal like matrix. It will become clear soon, of shape M cross N. And V is another orthogonal matrix. Is an orthogonal matrix.
N cross N.
Yeah, of shape N cross N. Okay, so this is guaranteed to exist for any matrix A. Okay, so the first thing that you'll have to realize, which is very important, is every matrix has a singular value decomposition. So no matter what, okay, so recall that only square matrices, that too only diagonalizable square matrices, have an eigen decomposition.
Decomposition.
Okay, so this is very important. So this eigen decomposition, PDP inverse QDQ transpose, whatever it is, you can only do it if the matrix is square. Okay, and that too square diagonalizable. So it's very specific instance. Okay, if it is otherwise, you can't do an eigen decomposition because eigenvalues, eigenvectors are themselves not defined for rectangular matrices. Okay, so we have to fall back on what is called the singular value decomposition. So I'll call this SVD theorem. It's a very, very fundamental theorem, fundamental result in linear algebra. So in fact, one of the textbooks, what it says is that if you know SVD, if you can completely understand SVD, then you have like understood linear algebra. Okay, because the SVD is so powerful that you will see that most of what we have learned can be obtained very, very easily by looking at the singular value decomposition of a matrix. Okay, so is there any question regarding the statement of this result, of this theorem? Okay, right. So let's now the whole next half an hour, what we'll try to do is, how do we obtain this decomposition? So it's one thing to say that it exists. So what does this theorem tell you? It tells you that there are these three matrices, but then it tells you nothing more. It doesn't tell you how you can get hold of these matrices, right? So And so that is what we are going to look at next, right? So the next question is,
Sir,
yeah.
sir, is this U is a unitary matrix? Because
Yeah, so if you are looking at a complex matrix, yes, U and V are unitary. So there's a complex version you can write, which is U sigma V star. Okay, I'm just sticking to the real version here, but yeah, you are right.
okay, sir. Yeah.
The SVD theorem for real matrices, I'll just put it that way. Okay, so next question is, how do we compute U? So this is sigma, right? And V. Okay, how do we compute U sigma and V? So that is what we are going to do. But if you want to understand that, you have to understand something about these two matrices. Okay, these two are the key to understanding how to compute U sigma and V. Okay, so we will study the matrices A transpose and A transpose A. Okay, so this will help us derive the singular value decomposition of A. So that's the T. So that's why we are studying A transpose A and A transpose. Okay, mainly we are going to look at some properties. These properties may seem totally disconnected now, but each of them will be used in a particular way. Okay, so property one, I'll just call them properties. Property one is first is a very simple one, right? So A transpose A and A transpose are what kind of matrices?
Real symmetric.
Yeah, they are symmetric. Okay, so that is the first observation. I hope you're all able to see that. So if you do, there's nothing hard here. So if you do A transpose A, the whole transpose, this is nothing but A transpose A. Okay, likewise A transpose, if you do the whole transpose, order swap, and you still do the transpose, right? So they are symmetric. Okay, so this is clear enough, I believe. Property two is the following. Okay, so A transpose A, and let's first look at the shape. So in between, we'll just, so let us look at the shapes of these matrices. So this is important. So what is the shape of A transpose A? Is it M cross N, N cross M, M cross M, N cross N?
N cross N.
So M cross M.
Yeah, N cross N, right? So
Yeah.
so let's start with let A be an M cross N matrix, right? We'll make that clear. So A transpose is N cross N, and A transpose is
M cross N.
it's an M cross N matrix. It's an M cross M matrix, right? So this is important. So once this is out of the way, then we can start talking about the property. So the properties are that it's symmetric. So the second property, which is very important, is A transpose A and A transpose have non-negative eigenvalues. Okay, so this is the second property. Let's just show this for A transpose A. Okay, and I won't do this. I won't prove everything because we may not have time, as I said. So let's just show this for A transpose A. It is automatically true for A transpose, right? You just need to replace A with A transpose and it will be true for A transpose. Okay, so it's enough if you show it for one of these two. So as usual, let's start with let lambda be some eigenvalue, eigenvector, okay, pair for A transpose A. Okay, eigenvalue. So what do you know if they are eigenvalue eigenvectors for A transpose A? First equation that you can write. A transpose A
Transpose A lambda. A transpose A lambda.
into V, right? So V is the eigenvector, right? So this is what?
Lambda V.
This is lambda.
Lambda.
Okay, so this is lambda V. Now, what do you want? You want to show that lambda is always positive. So what we do is we multiply both sides by V transpose. So why do we do that? Because if you multiply by V transpose, you get V transpose V on the right hand side, which is actually useful. So what I'll do is I'll first rewrite it as, I'll just swap the LHS and RHS. Okay, so this will become clear why we are doing. So it makes life easy. So now if you multiply by V transpose on both sides, you will end up with this is equal to V transpose A transpose A into V. Okay, and you can rewrite this as V transpose, you can just expand. So V transpose A transpose AV. So what is this together?
AV transpose.
AV transpose.
Yeah, so it's AV transpose AV. And what is something transpose something?
Square.
Yeah, it's the norm square, right? So remember X transpose X is norm of X square. So now you notice that now V transpose V is actually positive because that is also norm V square and V is not equal to 0. So V not equal to 0, right? So it's an eigenvector. So V can't be 0. So now V transpose V is positive. And norm AV square, that's the length of some vector, right? It's also positive. Therefore, lambda is
Positive.
Positive.
right. So actually, it's my small catch here. So you should not call positive. You should call non-negative, right? It could be 0 for all you know. AV could be 0. So therefore, you can't say that it is exactly positive. It could be 0 also. Therefore, lambda is greater than or equal to 0. That's what we want to show. So A transpose A and AA transpose have non-negative eigenvalues. Okay, so this is important. You could also note that since we have done positive definiteness, also note that both A transpose A and AA transpose are what kind of matrices?
Positive.
Symmetric square.
Positive. Yeah, positive.
They are positive semi-definite, right?
Semi-definite.
Yeah.
Okay, so A transpose A and AA transpose are positive semi-definite matrices because they have non-negative eigenvalues. That is one way of seeing. So, but anyway, so that is property 2. Okay, this is also needed. Property 3, okay, is the following.
Someone's please show property number 1.
Yeah, property 1 is just that they are symmetric.
Yeah, thank you.
Okay. Okay, so next one is what? So A transpose A and AA transpose miraculously have the same positive eigenvalues. Okay, that's a very nice connection between the two. So they have the same positive. Not only are the eigenvalues non-negative, they are actually the same for both of them. The positive eigenvalues, right? This is important. So it's all the eigenvalues are not the same, but then the positive eigenvalues are the same. Okay. So I'll just very quickly. This also it's important to prove this. It's a useful proof to have. So I'm going to go ahead and prove this also. So we once again start with some eigenvector pair. Okay, so lambda comma v. So this part remains the same. So let lambda v be some eigenvector pair. So that remains the same for A transpose A with v not equal to 0 because it's an eigenvector. So we once again start with A transpose A v equal to lambda v. Okay, see now what you want is you somehow want to introduce AA transpose into the equation. Okay, so if you want to introduce AA transpose into the equation, what can you do? What is one thing we can do?
Multiply by A.
Exactly.
Multiply by A.
Exactly, that's correct. So you can multiply by A on both sides. You can pre-multiply by A. So to bring AA transpose into the picture, pre-multiply or left multiply. Pre is not clear. Left multiply by A. Okay, on both sides. So what will that lead to? So you will get A transpose A. Remember, I'm just expanding the bracket. So, and I group it like this. Okay. So A transpose A into V equal to lambda times AV. Okay. So now what do you observe?
Lambda equals to A transpose equals to A, so lambda equals to A square.
Okay. So this is something into something equal to lambda times something. That means what?
AV is an eigenvector.
Exactly. Right. So AV is an eigenvector of AA transpose with eigenvalue
Lambda.
Lambda.
lambda, right? So actually this statement is, you need to qualify it provided AV is what?
Not 0.
Non-zero, right? So I'm not going to show this now. It is not hard to see this. There's only one step. Okay, so this I leave it as exercise. So show why AV is not equal to 0. This is true. So AV is not 0. So you can show that. I leave that as an exercise. In case you are not able to figure that out, we can discuss it next session. Okay. So AV is an eigenvector of A transpose with eigenvalue lambda. So that's what we wanted to show. In fact, okay. So yeah. So there is one more line right here. So such that lambda greater than 0. So we have to start with this. So this lambda greater than 0 will be required if you want to show that AV is not equal to 0. Okay, that's where the catch is. So this is important. So what we have now shown is, if lambda is an eigenvalue of A transpose A, lambda is also an eigenvalue of AA transpose. So what we have shown is, if lambda is an eigenvalue of A transpose A, then lambda is an eigenvalue of AA transpose as long as lambda is positive. Okay, so we have only shown one direction. For those of you who are able to see that, you also have to show the other direction. So every positive eigenvalue of A transpose A is an eigenvalue of AA transpose, but ideally you should also be able to show the other direction. But anyway, so just give me 1 minute. I'll be back. Just 1 minute. I'm sorry for the delay. So yeah. Okay, so that is where were we? So A transpose and A transpose A have the same positive eigenvalues. Okay, so that is there. Okay, so is that enough? So there is one more property that I would add, and then we can move on to the SVD. So this is property 4, right? So what is property 4? Property 4 is the following: A, the matrices. Okay, the rank of the matrices A transpose A, and A transpose are equal. That is, if A has rank A, okay, or rank R, then rank of A transpose A and A transpose is equal to R. Okay, so this I'm not going to prove. This is quite involved, the proof. So I will leave this out, but all these are important. Okay, so they are needed for us to understand this SVD. Okay, so any questions so far in this section on A transpose A and A transpose?
Sir, one question.
Yeah.
So suppose if the eigenvalue of A transpose A is 0, we cannot comment that it will be same for the A transpose A transpose. Is it?
Sorry, which is 0?
A transpose A.
If one of what is A 0? Sorry, can you repeat that?
eigenvalues, 2.3 properties.
Okay, 2 and 3. If one of the eigenvalues of
2.3 properties, third one.
2.3, okay.
This one, sir. This positive eigenvalues, if it is 0, then we cannot comment both will have same 0 eigenvalues, is it?
See, the eigenvalues can either be positive or 0, right? Because we have shown in the previous property that they're all non-negative, so they can only be positive or 0. So all of them which are positive are shared between the two matrices.
Okay, and if it is 0?
0 they will have, right? So they can have 0 eigenvalue. So that will not be equal because that need not be equal. See, this is n cross n, so this has n eigenvalues. This has m eigenvalues. So if okay, so I'll maybe add one more property and close this part so that will make it clear. This is what? This is A transpose A and A transpose have R positive eigenvalues where R equal to the rank of A. Okay, so we have shown in the previous property that A transpose A transpose we have not shown, but we have just mentioned that they have the same rank. Okay, so for diagonalizable matrices, the number of positive eigenvalues is equal to the rank. This is something very important. Unfortunately, we have not discussed this anywhere in the course, but yeah. So if you have a diagonalizable matrix, A transpose A transpose are all diagonalizable. Okay, so it will have R positive eigenvalues where R is the rank of A or rank of A transpose A transpose. Okay, therefore we can conclude the following: A transpose A will have, remember A transpose A is of dimension n cross n, right? So it will
N
have
cross
A
n.
minus R 0 eigenvalues, right? Meaning it will have eigenvalue 0 repeated n minus R times. A transpose will have m minus R
minus
0 eigenvalue. Okay, so therefore also. So is this clear to everyone? This I'm not giving you the proofs for these. So if you want to see the proofs, I can link it in the notes later.
So means none of the A transpose A and A transpose guarantees invertibility.
Yeah, so they need not be invertible. So they'll be invertible only if this is 0, right? There are no 0 eigenvalues.
Sir, so this means that suppose m is less than n and the rank is R, so there will be m positive eigenvalues and the remaining will be zeros, is it?
Yeah, so see, rank is always going to be less than m minimum of m and n. So whatever, so for example, if you have say 10 cross 7 matrix with rank 2 1x, for example, if A has rank 4 and is of shape 10 cross 7, let's say, okay, then A transpose A will be of shape what? 7 cross 7, right? It will have 7 eigenvalues in total. So it will have 3 0 eigenvalues. And A transpose will have how many?
6.
6, 6,
Yes.
Yeah, 6 eigenvalues, right? So 6 0 eigenvalues.
correct.
This is what
Got
we
it.
are claiming. Okay.
Got it.
Okay. So that is SVD derivation is the next one. Okay. So I'll very soon move to examples. If all this theory is not your cup of tea, we'll go to examples soon. But this theory is required. Otherwise, we can't understand the process behind SVD. So let's start, right? We will work with either A transpose A or AA transpose, right? Depending on which of m n is smaller. Okay, so this will become clear when we do this example. Okay, in this example, AA transpose is of what shape?
3 by 4.
3 cross
3
3,
cross
right?
3.
So A transpose is 3 cross 3, A transpose A is 4 cross 4. So whichever is smaller, we will work with that matrix. So in this case, we'll work with AA transpose. Here it doesn't matter because they are anyway square. But in general, if you want to derive the SVD, it's convenient to take a smaller matrix. So whichever of m and n is smaller, we will take that particular version. Okay. For this section, we will work with A transpose A, right? So the results are the same if you do with A transpose also. Okay. Yeah. So first thing is, so recall. So I'll once again recall that we are looking at U. So A equal to U sigma V transpose, right? So this is what we want to derive. There are three things that we have to find out, right? One is U, another sigma, another V transpose. So we'll start with V, okay? And then we will see that sigma emerges, U also emerges in the process, okay? So the first thing is, yeah. So we'll start with A transpose A's eigenvalues and eigenvectors. So consider an eigenvalue lambda with eigenvector V for A transpose A. Okay, so this is where we are starting. So A transpose A, you already know what this means. A transpose A into V equal to lambda times V. Okay, so now since A transpose A has rank R, it will have R non-zero eigenvalues. So let us call them lambda 1 greater than or equal to lambda 2, so on and so forth till lambda R. Okay, is this clear what I have done here? I have arranged the eigenvalues of A transpose A, all the positive eigenvalues of A in decreasing order, and there are R of them. Is this okay with everyone?
Yes, sir.
Okay, so once you have done this, let's take one particular eigenvalue. So A transpose A Vi. So when I say Vi, it could be and okay. So let so V1, VR be a orthonormal collection of eigenvectors corresponding to these eigenvalues. Okay, what does that mean? First of all, does this always exist? Can we always find an orthonormal collection of eigenvectors corresponding to these eigenvalues? Yes, no,
Yes.
yes.
Yes, sir.
Okay, can you tell me why? Why is this case? Why is this the case?
Because they correspond to different eigenvalues, so they are orthogonal, and we can divide by norm to make it orthonormal.
Okay, but they are not necessarily distinct, right? So they could be same. So I'm saying that they are greater than or equal to.
But sir, A transpose A is symmetric, so symmetric matrices will always have distinct eigenvalues, no?
Not necessary, right? Symmetric matrices need not have distinct eigenvalues. They could have repeating eigenvalues. Symmetric matrices have something else, right? Which we have studied yesterday. They are orthogonally diagonalizable, right? So they will have a basis of
Orthonormal. Yeah.
yeah. So they'll have an orthonormal base Rn, right? Will have an orthonormal basis of eigenvectors. Okay, so okay, maybe they will just erase this. So see, this is the reasoning. Since A transpose A is symmetric by some theorem which we studied yesterday, A transpose A will have, or rather R, so Rn, right, will have a basis of orthonormal vectors, right? That are what eigenvectors of A transpose. Okay, what is this theorem that we studied yesterday which guarantees this?
Spectral thing.
Spectral.
Yeah, so by the spectral theorem, you will have eigenvectors that are orthonormal. Okay, so is this clear to everyone? This is like
Yes.
important. Okay, so you have, therefore, so how are we going to call that? We are going to call, so lambda 1, so A transpose is n cross n, right? So I'm going to order them in decreasing order. So I'll keep going on like this. I'll call this lambda r. So there are r, so also A transpose A as r positive eigenvalues, okay, and the rest are 0. So I'm going to call them lambda 1 to lambda r greater than or equal to lambda r plus 1. Okay, so this is dot 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 till lambda n, which is equal to 0. Right? So is this clear what I have written here? I have arranged them in decreasing order. So first r could be all equal also. It doesn't matter. But then they are arranged in a particular order. From lambda r plus 1 to lambda n, they are all 0. Okay? And then you have a basis of eigenvectors. So that is what? V1 till Vn. Okay? Is an orthonormal basis for Rn. Okay? So that is, if you do the spectral theorem decomposition, or spectral decomposition, this will be nothing but, so let's put all these n vectors into the columns of a matrix V. Okay, so the matrix V is what? Now what will this V look like? Be V1 dot 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 Vn. Okay, there will be n cross, there's an n cross n matrix. All the columns are the eigenvectors. So let's put all these n vectors into the columns of a matrix V, and all the n eigenvalues into a matrix D. Okay, what you will end up with is D equal to lambda 1 here. Okay, lambda n. Okay, this is, let me know if this is clear to all of you. So this is what? A transpose A is equal to V D.
V inverse.
Yeah, V inverse is nothing but
V transpose.
Transpose.
V transpose, right? Because this is orthonormal, this is an orthogonal matrix. So V is orthogonal. Okay, so all this comes from the spectral theorem, which we studied yesterday. Okay, so let me start from here. So recall that. So this is what we are trying to. So this step is building V. This is the first step that we have done. So we are building V here, and you have actually built V. So whatever V that you are going to see here is nothing but the eigenvectors of A transpose A. Okay, so VD V transpose. Is this clear so far? We have actually constructed V. Okay, so now we are going to construct U. So for this construct, okay, so before we go there, I just want to add that norm Vi is equal to 1 and Vi transpose Vj equal to 0 for I not equal to j. That's what it means for it to be orthonormal. Okay, so that is mentioned there. Okay, so to construct U, we consider this eigenvalue eigenvector pair lambda I comma Vi for some I in 1 to R, right? So remember that A transpose A and AA transpose have the same positive eigenvalues. So lambda 1 to lambda R are the same. So if you look at A transpose A into Vi, this is lambda I Vi, correct?
Yes, sir.
Okay, so now whatever we did before, right? You multiply by A on both sides, so you get A transpose Vi equal to lambda I into AVI. Okay, so there's one A missing here. So AVI. Therefore, AVI is an eigenvector for AA transpose. So what we are going to do is we are going to define UI, okay, as AVI by sigma square. So sigma. So that is we need sigma. So one more step. Okay, so just stay with me. Since these lambdas are positive, so V is constructed. So we'll build, before we build U, it's easier to build sigma first. Okay. So how do we build sigma? So notice that lambda I is greater than or equal to 0, right? For any I. Okay. So we are going to define what are called the singular values. Okay. Sigma I. So corresponding to lambda I, you are going to define a sigma I such that sigma I square equal to lambda I. Okay. Or what you can say is sigma I, you can define it as square root of lambda I, positive square root of lambda I. Okay. So sigma I is called the I singular value of A. Okay. So what can you tell me about? So note that. What can you tell me about the relationship between sigma 1, sigma 2, and so on? We can order them, right? So sigma 1 greater than or equal to sigma 2.
Descending order.
Yeah, in descending order till sigma r. So what can you say about the first r singular values? They are
Positive.
Positive.
they are all positive. Okay, so they are all positive. So these are greater than 0, where r, always remember, is the rank of the matrix A. Okay, and sigma r plus 1 equal to dot
0.
dot equal to sigma. Okay, so here is one tricky thing that will come up when you are solving for the SVD. What could be the last singular value? Is it m? Is it n?
N, sir.
Okay, right. So this is a bit tricky. So this is usually you can't figure out. So what you have to do is you have to take this as the minimum of m comma n. So if there are, if you have an m cross n matrix, right? So if you have an m cross n matrix with rank r, it has r positive singular values and min of m comma n minus r 0 singular values. Okay, so why is this the case? Let's take one example, it will become clear. So if you are working with a, say, 10 cross 7 matrix, okay, let's say the rank is, in this case, 4. Okay, so rank is 4. Now there will be 4 positive singular values, but remember that A is what? A is sigma A. This is what we are trying to do. So sorry, A is U sigma V transpose. Okay, and sigma, we told, what is the shape of sigma?
10/7.
This is also 10 by 7. Okay, so
Sigma
sigma is,
should be a square matrix, right? 7 cross 7.
sorry,
Sigma should be a square matrix, right?
no, sigma is not a square matrix, so it is actually m cross n. Okay, so how many sigmas will be there? There are 10 rows. there are 7. So all the sigmas are going to go on the diagonals.
7.
7.
7.
Okay, if you change it to 7 cross 10, if you change it to, if you look at some other matrix, let's say 3 cross 10. Okay, if it is 3 cross 10, how many singular values will it have?
3.
3 only.
3.
Okay, so you can kind of think of this as tall matrices and fat matrices. So this is like, this is fat matrix. Okay, or maybe wide. Let's not use that word. Wide matrix, and this is a tall matrix, right? So this one will be a tall matrix. So this is, so this is a tall matrix. Okay, so tall matrix will look like this, and a wide matrix will look like that. So this is the case where m is less than n or m is greater than n.
When rows are less than.
Less than
N.
n.
So this is m less than n. So wide matrix is m less than n case, and this is m greater than n case.
Yes. Row and column matrix.
Yeah, something like that, but not necessarily a single row, single column. So the diagonal, this the singular values, okay, the singular values go into the diagonal of this matrix. So singular values occupy the diagonal positions, diagonal positions of sigma. Okay, that's what. So if you look at S sigma, sorry, S, it will look like this. It will be a diagonal like matrix where this will be sigma 1, this will be sigma 2. Okay, so this is dot. So still sigma r will be positive, and then sigma r plus 1 will continue, and this will once again keep going. So this is e dots array. What is this? Yeah. Whoever is not talking, can you please be on mute? So this is minimum of m comma n. So this will become clear soon. So this is a diagonal. That's what I meant by. So it is a diagonal like matrix, right? It's not exactly diagonal because it's not square. Okay, so it's m cross n. So if you come down here for a wide matrix, what will happen is more of geometry, but it's fine. Helps us. So that, notice this is how sigma. So the line represents all the diagonal entries in sigma.
M only. Only M singular values should be.
Yeah. So this is a square, by the way, right? So for those who can see, I'm just making it a dotted line. This is not a part of the matrix. In fact, it's not even a matrix, but I hope you understand why we are doing this. So this is just to give a sense of some visual picture of how sigma is going to look like. So this will go till what? This will go till
Number of columns on this one.
sorry.
It will not go to till the end, right? It will go somewhere in the middle.
Yeah, sorry. This will go till wherever this is square, right? So
Yeah.
maybe here.
Yes, it makes sense.
Okay, so you make that. So it is essentially what? So this is, yeah, m cross n, right? So I'll add some more details so that it becomes clear. So m is less than n. So this is m. This is m. This is, what will the remaining number be?
N minus M.
N minus M.
Minus m. So in this case, minimum of m comma n is equal to
M.
right?
M.
So there will be m singular values here. So in that, for a wide matrix, you will have m singular values. Okay, so for a tall matrix, you will have how many?
N.
N, right? So this is M, this is N, and this is also N, correct? And this is whatever portion remains is minus N, correct? Only, no, whatever we are doing.
Yes, sir.
Yeah, okay, right? So this is tall matrix. So a tall matrix will have minimum of M comma N is N. So this will be N singular values. Okay, so that is, so in either case, it will be minimum of M comma N. So for a wide matrix, it will stop, it will go all the way till the last row. For a tall matrix, it will go all the way till the last column. Okay, that is what we have. So we have built B, sorry, sigma. So this is build sigma, this is building V. So V, how did we build? Just to recap, we took A transpose A, did the eigen decomposition of A transpose A, that gave us V. Okay. Now, how do we build sigma? You take the eigenvalues of A transpose A, okay, and you take the square root of the eigenvalues of A transpose A, and you call them the singular values. There will be minimum of M comma N such singular values. R of them will be non-zero, and they are called the positive singular values. So they will occupy the first R cross R, so diagonal part of sigma. The rest of the diagonal elements will all be zero. Okay, they are the zero singular values. Okay, so far, are there any questions? How do we construct how do we construct V and sigma? Any questions in these two sections?
Sir, is it necessary that while constructing V, we have to take the eigen decomposition of A transpose A and not A transpose?
That is not needed. So I mean that it's not. It depends on. That's what we started off with, right? So we will work with either A transpose or A transpose depending on whichever is smaller. So you can do with. You can start with either of them, but starting with the smaller of these two will help you. It will make life simple. Okay.
Okay, sir.
Yeah, any other questions? Does anyone else have any other questions?
Sir, A transpose A is N cross N matrix, right, sir?
Yeah, A
Even A
transpose.
is M cross N.
Yeah, A transpose is N cross N, A transpose is M cross N. Okay.
So, sir, one confirmation I need from you, sir. Like if we start with the smaller ones, we get all the eigenvalues, and for the bigger matrix, the same eigenvalues will be follow that bigger one, and the remaining will be zeros.
Zeros, correct.
Okay.
Any other questions regarding these two sections? Building V or building sigma? Okay, right. Then we'll go and build U. So yeah, this is where it is slightly challenging. Till this, it's actually quite easy. Okay. So how do you build U? So this is yeah. So you first notice that you are AV, right? So I'll just state this and then we'll see why this is true. Consider the following assignment. Okay, so the elements of U, I'm going to call U1, U2, U1. So we want to construct the following orthonormal matrix for n cross n made up of, okay, made up of will come later. So what is U going to look like? Not n cross n, m cross n, right? So this is U. So U is m cross n. So the columns of U are going to be U1 to UM. This is what we are trying to construct. Okay, so these have to be orthonormal, right? Now consider the following assignment. This UI, okay, is equal to, when I say colon equal to, it means that I'm assigning, but you can also have it as just equal to A times VI, Okay, so I can multiply A and Vi, right? So Vi is, remember this Vi. So whatever Vi we had as the eigenvectors, right? So that is n dimensional. So you can multiply A and V. If you multiply, yeah, sorry, there's some noise. So if you multiply A and V, what is the dimension of the vector that you will get? A and V. So A is m cross n, V is n cross 1. If you multiply them, what will you get?
M cross 1.
Yeah, you will get m cross 1. Okay. So now what you are doing is dividing this by
M cross.
yeah, m cross 1. Yeah, correct. Right. So Ui is equal to AVI by sigma I. So this is what we are going to do. And this will be one of the UIs. Consider the following assignment for what should be what should I be less than or equal to?
M.
Is it M or is it something else? What can you say about sigma R plus 1 and sigma till sigma M?
R it should be.
It should be
R.
R, right? Because since these are the only positive eigen singular values, right? So you have to be careful when you are dividing by sigma I. Okay, so we will see what the others are soon, but this is what you have now. So what is the first thing you check now? If I say that this is U1, U2, you should ask me two questions. I claim that the first R columns of U are these R vectors. So if that claim is true, what are two things that you'll have to check?
So that they are unit vectors and they are orthonormal.
Yeah, exactly. Right. So check if, first of all, U1 to U1, UR are orthonormal. Okay. We'll then worry about how to get UR plus 1 to UM, but first we'll worry about this part. So you have to check if they are orthogonal first. Okay. So what is UI transpose UJ? It is AVI transpose AVJ by what will be in the denominator?
Lambda I.
But if you have defined it this way, right? So it will be
So lambda I, lambda j.
sigma I, sigma j, right? So I have defined it as sigma
Yes, yes,
I.
sorry. Sigma I.
Okay. So what next? What can you?
It's 9 o'clock.
What is the numerator going to become?
So Vi transpose A transpose.
Vi transpose A Vj. Okay. Sigma I, sigma j. Okay. So now, yeah. So I'm going to write this as Vi transpose A transpose A into Vj. So what is A transpose A into Vj? What is Vj?
So lambda Vj
Yeah, Vj is an eigenvector of A transpose A.
of A transpose A. Yes, sir.
Right, so this becomes lambda j Vj, correct?
Yes, sir.
Okay, so let's, in fact, you can show both orthogonal and orthonormal with this. So we have this expression. Now this is clear, right? So depending on what I and j are, so this one more step is there. I can write this as lambda I, so lambda j, sorry, Vi transpose Vj by sigma I, sigma j. Are you all with me so far?
Yes, sir.
Okay, so there are two cases, I equal to j, I not equal to j. So if I is equal to j, what will happen? Vi transpose Vi is what?
Norm square of
So
V.
norms.
Yeah, norm square of Vi. So what is norm square of Vi?
V square. Vi square.
1, right? Because recall that they are, while building V, we started with norm Vi is 1. Okay, so norm Vi square is 1. So there is a sigma I square in the denominator and there's lambda I in the numerator. So what will happen to them?
Cancel each other.
They will cancel each other, right? Because
They are equal.
they are equal, right? So lambda I is sigma I square. Okay, so Therefore, we see that it is indeed unit norm. What happens if Vi is not equal to Vj? Sorry, I not equal to j,
0.
0.
right? So recall that Va and Vj are orthonormal by construction. So we constructed V that way. So Vi transpose Vj is 0. Okay. So what we have arrived at is a very surprising result, which is that U1 to UR are orthonormal. Okay. So, and what you can now do is, complete U1 to UR to, or not complete, extend U1 to UR to UM, which is an ortho basis for Rm. Okay, we'll see how to do this in the example. So this will become clear when we do, I think, the second example, how to do this completion. Okay. So is this clear to all of you, what we have here? How did we get U1 to UR at least? Okay, so now this relationship is there, right? So which we have here. So now note that this is true only for 1 to R, right? I said this is true only for 1 to R. If you replace this as AVI equal to sigma I UI, the following relationship is, or the following equation is true for 1 less than or equal to I less than or equal to the largest index of the singular value, right? Why is this true? Why do you think this is true?
Because sigma I is not equal to 0.
Sigma I is not equal to 0 for 1 to R, okay? But for R plus 1, R plus 2.
It is 0. Sir.
So right hand side is 0. What about the left hand side? So if you go back, this is a slightly technical point. So okay, so in order to prove that, you need little more machinery, which I don't have now. I'll have to discuss few more properties here. But basically what it means is that VR plus 1 to Vn are actually, if you multiply A with them, it's going to be 0. Okay. So I'm not going into that part now. For those who are interested, I will share a detailed write-up of this soon. So this is to do from my side. So to do share detailed proof for this. Okay. But for now, please take note of this. We will look at this soon. So some quotation here. So U, whatever U we have obtained, right? U is called, or every UI is called the left. Is a left singular vector of A. Vi is called right singular vector of A. Okay. So do you see the reason it's called this is, so it's not an eigenvector clearly, because A need not even be square. But notice what is happening. A times some matrix is sigma times some other, sorry, A times some vector is sigma times some other vector. Okay. So this sort of looks like AV equal to lambda V. Okay. Therefore, even though you can't call them eigenvectors and eigenvalue, you can still call them singular vectors and singular values. And because U and V appear on two different sides of this SVD, right? So see where sigma and V appear. Since U appears on the left, it's called a left singular vector. Since V appears on the right, it's called a right singular vector. Okay. So is this clear so far? I've kind of hurried and not explained things properly here, but is this fine for everyone? Any doubts in this SVD equation? This is a very important equation. AV equal to sigma U. Okay, right. So that with that, what we'll do is let's jump into examples. Without that, we won't understand exactly what is happening. So for the next 1 hour, we'll do 3 examples mainly. Okay, so can we break for 2 minutes and start with the examples? Is that fine?
Yes, sir.
Yeah, thanks. Okay, so shall we start with the examples? Okay, thank you. So we'll start now. So I request some of you at least to do the calculation. So I will also be doing that, but I won't know where I'm going wrong. So it will be a great help if you can, have your some pen and paper with you and do the calculations on the side. Okay, so we'll start with step 1 is A transpose A. Okay, we'll start with the eigenvalues, finding the eigenvalues, eigenvectors of A transpose A. Or let me just call it V. Step 2. Step 1 is V. Step 2 is sigma. Step 3 is U. Okay, in the same sequence. So 3 steps, and that should give us U sigma V transpose. So for V, we are going to look at eigenvalues of A transpose A. So that is first you have to compute A transpose A. So quickly do that. So this is 3, 0, 2 minus 2, and 3, 2, minus 2, 0. Okay, what is this? 9 minus 4. 5, 6. 6. Is that correct?
Sir, it
Yes,
should
sir.
So that's 9 plus 4.
So it should be 13.
Okay, sorry, yeah. Correct, right? This is correct now?
Yes.
Okay, now for the characteristic polynomial of A transpose A. So that is the determinant of A transpose A minus lambda I. Okay, so this is what? This is 13 minus lambda 6.
Sir, instead of 6, it should be minus 6 now.
Oh, is it which 6 you are saying? This one, huh?
Yes, sir, this one.
3 2s are 6. 6 on 6 only, right? 3 into 2, 6 plus 0. 2 into.
Okay, sir, okay.
Okay. So this is what? 13 minus lambda into 4 minus lambda minus 36. Okay, this is lambda square minus 17 lambda, right? This 17 lambda 52 minus 36 is it? 46, 16. Correct? Is this correct?
Yes, sir.
Okay, so lambda minus 16 into lambda minus 1. Is that correct?
Yes, sir.
Okay, so the eigenvalues are 1 and 16 and 1. Okay, so that is one. This is step 1.1, if you want to call it that. So step 1.1 is computing A transpose A. Step 1.2 is computing the eigenvalues of A transpose A. Step 1.3 will be computing the
Eigenvectors of A transpose A.
A transpose A. Okay, so A transpose A, let's do step 1.3.1 will be for A lambda equal to 16. Okay, so this is A transpose A minus 16I into some V equal to 0, right? So this is A transpose A is what? This one. So let me copy that. This is A transpose A minus 16. So this will become
Minus
3.
3. This will become
minus 2.
minus 12. Okay. So now if you row reduce, what will you end up with? So let's just divide the first row by minus 3. So that will be 1 minus 2, right?
R2 is 2 times R1.
R2 is 2 times R1.
Minus 2 times.
Okay, you'll get 0, 0. Is that correct?
Yes, sir.
Yes.
Okay. So this is 0. So
Yes,
you
sir.
correct only, no? Whatever we have done so far.
Yes.
Yes, sir. Correct.
Okay. So this, let's make this V1, V2. So you are, can you tell me one eigenvector for 16?
2,
and
comma
2 comma
1.
okay, 2 comma 1 is an eigenvector for lambda equal to 16. Let's also normalize it because we want normalized eigenvectors. So this, if I normalize it, I'll get
Excuse me, sir.
Root 5.
yeah.
Sir, if you do R2 minus 2 times of R1, then in row 2 and column first, it will be 0. But row 2 and column 2, it should be minus 18.
So if you add 2 times R1 to R2, right? So this will be 6 plus 6. This will be minus 12 plus 12, right?
Okay, I was doing minus.
Yeah. So next one is A transpose A minus I. Okay, V equal to 0. So this is A is A again. A transpose A again. So this is 12, 3. Okay. So 12, 3. 12, 3. This is what? Once again, this will be 0, right? We can make this 0. 0, 0.
Yes.
And like we can make this 2 and so for
2,
convenience.
1.
Yeah,
2
let's make
and
it
1.
2 and 1. And V1, V2, 0, right? So this is 0 vector. Now, one more normalized eigenvector, can you tell me?
1 minus 2.
1 by root 5 into minus 1, 2.
Yeah, 1 minus 2 minus 1 2, right? Both are correct. So both are correct, right? 1 minus 2, yeah, 1 minus 2, yeah, 1 minus 2 by root of
5.
By root 5.
okay. So it's a unit norm. So it's a unit norm eigenvector for lambda equal to 1, right? 1 was the eigenvector, yeah, 1 was the eigenvector.
Sir,
Okay.
0. No, sir, 1. Yes.
Right. Yeah. So step 1, yeah. So now V. So all that we have is V. Remaining is we have to enter V. So we just enter this thing. So it is 2 by root 5. So I'll take 1 by root 5 outside, and I'll call this 2 comma 1, and this column is 1 comma minus 2. Okay. So is this clear how we obtain V?
Yes, sir.
Okay. So this is V. Now step 2 sigma is easy in this case because it's everything is 2 cross 2. Okay. So sigma is just the eigenvalues, the square root of the eigenvalues of A transpose A. So let's maybe compute that as follows. So sigma 1 and sigma 2 will be what? Sigma 1 is under root
4.
lambda.
4.
This is what?
4.
16.
And lambda 2 is
1.
1.
okay. So the singular value, the sigma matrix is just 4001. Okay. So that is done. Always see the singular values are always in descending order. So in case this comes in the exam and you write 1 4, it is wrong. Okay. So no, it's not wrong, but always in many applications you will see that this convention is followed. Okay. So step 2 is done. Step 3 is what you have to find U. So we make use of the relationship A V equal to sigma U, correct? So U is UI is AV by API by sigma I, right? Here you can do that because all singular values are positive. None of them are 0. So you can get hold of all the U's in this way. So using this equation, we have let's first compute U1. So U1 is AV A. So first we need to get hold of A. Where is A? So this is A. So was A, right? So A times V1. So V1 was what? This one 2 1 by root 5. So 2 comma 1 by root 5, right? So this is 2 1 by root 5. I'll put the root 5 here. Okay. So this will be what? This will be some vector 6 plus 2 8, correct? 8 and minus 4, is that correct?
Yes.
So it's 1 by root 5. I'll take the 4 outside. So this becomes okay. Should I take the 4
By
outside?
4 root 5, no?
What? Sorry, what happened?
Sigma is 4 root 5.
4 sigma.
Because we did not divide by sigma I in this case.
Right. Sorry. Correct. Fine. So 1 by what was 4, right?
4.
1 by
Maybe sir,
4.
we can divide this 4 into 8 and minus 4. We reduce it.
Yeah. So yeah. Sorry. Wait, once again, I'll just move these things to the other so that it becomes less cluttered. So this is 1 by 4 sigma I into AVI, correct? Right? No.
Sir,
So
in that
matrix will be 2 minus 1.
2 minus 1.
2 minus 1, correct?
Yes, sir.
Extra 4 is over there, sir.
Yeah.
In
Sorry.
the numerator of root 5.
Okay. Got it. So it is now what? 1 by root 5 into
2
2
minus
into
1.
minus 2 minus 1.
okay, 2 minus 1. So 1 by root 5 into 2 minus 1. Okay, so that is done.
Sir,
Now-
there is a correction over there, sir. In the numerator of root 5, there's the extra 4 is present. Yeah, in the second distinction.
Here, right?
In the
Here
second
or
distinction.
second?
Yeah. This 4 will not.
This 4 should take as common because inside the matrix there was 8 and minus 4.
Yeah, minus 4, right? That is why we took this out.
Okay.
Okay. Okay, so A U2 is likewise A V. So A is this. This is A, right? No, this is A. This is A. I'll forget sigma again. So 1 by 1 in this case. Thankfully, it is 1. So 1 by sigma 1. Sorry, 1 by sigma 2 A. V2. V2 was what?
1 minus 2.
Yeah, 1 minus 2 by root 5. So 1 minus 2 by. See, this root 5 I'm writing outside. You must not get confused. It's just that having the root inside is cumbersome. Okay, so this becomes what?
Minus 1 minus 2. Outside there is 1 by root 5.
Okay. Minus 1 minus 2, is it?
Yes, sir.
Yes, sir.
Okay. Okay, great. Okay, if two of you confirm, I'll go ahead. Okay, that will save a lot of time for us. So minus 1 minus 2 by root 5. So this is quick check, right? This should be orthonormal. So this is already orthogonal. This is already unit norm. 2 minus 2. So this is minus 2 plus 2 0. Okay, so you can just quickly check that they are indeed orthonormal. So that is step 3. Okay, that's all. So we now have A. So A is what? This was A, right? So this is A. No, we didn't construct U. So U is first we'll construct U. U is nothing but again 1 by root 5. I'll put it outside. It is 2 minus 1 and minus 2. Okay. So finally you have A equal. So A is what was A? This was A. Is it 3 minus 3 2? Yeah, this was A equal to U sigma this one. Okay, and V transpose, right? So that is tricky. So we have to just make A, write down V here. So this is V. I'm going to bring in some ugly looking bracket.
Here V is symmetric.
Good point. Yeah. Interestingly, it is V is
Yes,
symmetric.
but every time it will be not.
Yeah, every time it won't happen. Yeah, good point. So it's not necessarily symmetric always. I'm also surprised. It so happens that it is symmetric, but so this is an example of a symmetric and orthogonal matrix, something that's non-trivial. It's correct now, whatever you have done. So this is orthogonal, right? 2 into 2, so 2 into 1 minus 2, 0. This is unit norm. Yeah, so this is a very interesting example of that, something which is symmetric and orthogonal. So in this case, V transpose, we didn't have to do anything. But this is not always the case. Okay, so we'll do. Let's do one more just to get a sense of. This will be slightly different because here you will have. I think this is not full rank. So this was full rank. Therefore, you didn't have to do anything for getting U1 and U2. So here you will have to do some work. So this is a slightly different example. That's why we are doing this also. So let's look at V, right? So step 1.1 is computing A transpose A. A transpose A is, you must help me here. So this is going to be a big mess. When you do A transpose A, diagonal elements don't change, right? Only Aij.
Yes, a diagonal element will not be changed.
Is this correct? A transpose A?
Yes, sir.
Yes, sir.
Okay, so this is A transpose A. Now, my God, we have to compute this. Let's do it. So it's fine. In the exam also, you'll be doing this. So if two of you can confirm each element, then we can
The
quickly
first
do it.
one is
11,
11, sir.
11.
11.
Okay.
8.
8, I guess.
Okay.
5.
Okay. This is also
8,
8. This is 5.
8.
This is also 8, is it?
Yes, sir.
Yes, sir.
Okay.
This is also 8.
This is also 8, sir.
It's also 8. Oh. Okay, what is the last one?
8.
11.
11.
11.
Last
11
one
or
is 11. Yeah.
11, sir. 11.
11.
Oh my god, yeah, so many 8s and 2 11s. Is to step 1.2 is the characteristic polynomial. So a minus lambda I is what is going to be. Are we sure this is A transpose A? It looks very horrible. Eight minus lambda 8, and then 5 8 11 minus lambda. Okay, does anyone have the courage to factor this? This is 11 minus lambda into what? 8 minus lambda into
8 minus lambda into 11 minus lambda minus 64 minus 8.
should we do this? But if we don't do this, we won't understand some important things. Can anyone do this and tell me?
Okay, sir, give me 1 minute.
Yeah, so it's okay. Let's take some 2-3 minutes and
I have got two values. One is 0 and second one is 6.
okay. Yeah. So
Third one I'm check.
yeah, that's correct. So 0 6.
Third one
Okay, so this is, yeah, I think I'm wasting your times also. So
is
you are
it
correct.
20?
Yeah, that's correct. Yeah. So I'll just I'll have the book from which I took this. I have it beside me, so I'll just refer to that without wasting all our times, because this is just computation. There's just algebra. It's boring and shouldn't have to spend so much time on algebra. So yeah, these are the eigenvalues. I'll also write down the eigenvectors for you. So okay, so there are 3 distinct eigenvalues. So note that in this case, rank. What is the rank of A?
2.
This
2.
is 2. Okay, so rank of A transpose A is 2, and the rank of A is also 2, because we have already seen the property that A transpose A and A have the same rank. So uh, this is where you'll have a problem, which I was mentioning, right? So you can't simply do AV by sigma for all 3 singular vectors. Okay, so you'll have to be careful here. So find the singular. So these are V, right? So step 1.3 is finding out V. So I'll write down the V for you. solving for A transpose A minus lambda I times V equal to 0 will give you the following. So it will give you V equal to, we'll just focus on the important part now. So you get V to be 1 by root 6. Okay, 1 by root 6 is all root 2. So is all root 2. And this is all minus root 3, 0, root 3. And this is minus 1, 2, 1. Okay, so I hope you all know how to compute this. This is just, you know how to do this now. Row reduction, that will give you three vectors. So this is clear, right? How we will, even though we haven't done it explicitly, I hope you know how to do this.
Yes, sir.
Okay, so step two is clear. So that is simple for us. This is the square root of the singular value. So they are root 24. Root 24 is what?
2 root 6.
2 root 6, and this one is
Root 6.
root 6 and 0. Okay, so that's the two non-zero singular values, and so step 3 is what I want to focus on. So step 3 is what? Getting U. So you can get hold of U1 as AV1 by sigma 1. Okay, this is all this you can do. You can also get U2 in this manner because sigma 1 and sigma 2 are non-zero. Okay, where you will face a problem is sigma U3. So I'll first write down what the author has obtained. So this is 1 by root 2 into 101 apparently. So 101. Okay, this is what? U2 is 1 by root 3 times 1 minus 1. Okay. Okay, so far these are orthonormal. So 1 1.
Sigma 2 was root 6.
Which one?
Sigma 2 was root 6, I think. Sorry.
Yeah, but this is AV2, right? So we are
Okay.
multiplying.
Okay.
Okay, so far you have obtained in your matrix U, you can now write down the first two entries. So this can be, if you take this as 1 by root 6, what will this be first?
Root 3, 0, root 3.
Root 3, 0, root 3. Everyone is seeing this, right? So I'm multiplying and dividing by root 2 so that there's a common root 6 here. So what will this be?
Root 2 minus root 2.
Yeah, root 2 minus root 2. Okay. Now what is remaining is the third column. Okay, third column, unfortunately, you can't just do AV by sigma because sigma 3 is 0. Okay, so you can't just do AV by sigma. So what should you do? What is the property of U3 that you have to exploit now?
It's going to be orthogonal to the other two and norm.
Correct. Yeah, since you are orthogonal to U1, U2 and has norm 1, we can find U2. Okay, so there are like a couple of ways to do this. One is, okay, so can someone tell me how to do this? What will you do?
Gram-Schmidt process.
Gram-Schmidt process is one, but if you, yeah, without going there, which is correct what you said, but what else can you do? If you want to find something that's just orthogonal, let's say.
Sir, if we assume U3 as ABC, it will be orthogonal to root 3, 0, root 3. Again, it will be orthogonal to root 2, and minus root 2.
Correct. Yeah. Okay. So that is one thing you can do. So you can solve a system of equation if you assume that. So the question is how. Okay. So if you assume that U3 is ABC, then what you can do is you have two equations and two unknowns. So first equation is it is orthogonal to this vector. See, it's actually orthogonal to 101. So you don't need the root 2, right? So you can, if it's orthogonal to unit norm vector, it's also orthogonal to 101, right? Any vector. So that will give you A plus C equal to
0.
Okay, and what about the next equation?
A plus B
A
minus
plus B minus C equal to 0.
Equal to 0, right? So from this, if you solve, you'll end up with, just tell me some solution. You can easily see one of these solutions.
1 0 minus
A equal to 1, B equal to 0, C equal to minus 1. That's the set workout. So 1 plus minus 1 is 0, 1 and 0. This one,
So B is equal to 2C.
so this one alone will not work out, right? Yeah. So
So A equal to 1, C equal to minus 1, then B should be minus 2.
okay, minus 2. So 1 minus 1, 0, 1. Okay, this works out, right?
yes, sir.
Okay, so you can, this is a skill that you have to develop. You can either solve a system of equations or you can eyeball, but eyeballing is a bit hard. You should find something orthogonal to this and also orthogonal to this. If you know Gram-Schmidt, all the more better, but Gram-Schmidt might sometimes take more time, but it's fine. This I would recommend you follow this method. So assume that it is something and then establish orthogonality and then orthonormal and then normalize. Okay. So what if you normalize, now normalize to get u3 equal to 1 by root 6, correct?
Yes. 1 minus 2 minus 1.
1 minus 2 minus 1, right? Now you can fill this. So it's 1 minus 2 minus 1. There is anyway a root 6 outside. So that is u. Okay, did everyone get this example? Why we did this example was to see what happens when you have one of the singular values as 0.
Sir, I have a question.
Yeah.
When we have U1 and U2, we already have 1 by root 6 outside of the bracket. So it should be 1 by 6 or 1 by root 6.
u1 and u2. So see, it was actually 1 by root 2, right? That is why we added 1 by root 6.
Yes, correct. But when we get U3 as 1 by root 6 into something, so that 1 by root 6 should come out.
It has come out, right? So otherwise we would have written 1 by root 6 minus 2 by root 6 and minus 1 by root 6, no?
You can look this way, like sir is dividing by root 6 and then multiplying root 6 by each of the elements inside the matrix. That's basically that cancels out the denominator.
Okay, sorry, I'm missing something. Can you? So,
Okay, sir. U1 is 1 by root 2, 1, 0, 1.
Correct.
U2 is 1 by root 3, 1, 1 minus 1. U3
correct.
we are getting 1 by root 6, 1 minus 1 minus, minus 2 minus 1.
Right.
Now, outside there should be 1 by root 2 into 1 by root 3 into 1 by root 6.
Oh, ma'am, we are taking 1 by root 6 common from the whole matrix. That is all the columns.
Yeah, that is what we are doing, right? So see, in fact, what was u?
Maybe sir, you can add one of the matrix where you can just.
Yeah, so I just add this. So this step was what? This was 1 by root 2, 0, 1 by root 2, right? So this was 1 by root 2, 0, 1 by root 2. And this was what? 1 by root 3. And then 1 by root 3. And then minus 1 by root 3. And this was 1 by 6 minus 2 by 6 minus 1 by root 6, right? So what we are doing is we are multiplying
1 by root 6 outside of the matrix, like common.
Yeah. So this is like root 6 by root 6 we are doing, and the 1 by root 6 stays in, the other root 6 goes inside. Therefore, you get.
Okay, got it. Thank you, sir.
Yeah. Okay, right. So this
Sir, a slide collection before how question mark.
How?
So that is, sir, the line above. Yes, so this is U3, right, sir?
Yeah.
We can find U3.
Yeah. Sorry, we can find U3. Yeah. Okay. So any questions? Any other questions so far in this part?
Sir, is there any?
Yeah, Utkarsh, continue.
Sir, is there any standard way to find UI if the corresponding singular value is 0?
Standard way.
So you
One
mentioned
thing,
AVI equals to lambda sigma IUI. Is
yeah,
that to
so
be used somewhere?
so AVI equal to sigma IUI you can only use for non-zero. This you can use only for non-zero sigma I. For zero sigma I, you have to go to either Gram-Schmidt or whatever we did now, right? So there's no other way. There's one foolproof way, so which I didn't mention, but I'll mention that soon. So that's what we'll do next. Properties. When we look at properties, we'll see that. Okay. So any other questions?
Well, I was having one question. Like in exam, what is the maximum size of matrix we can expect from this question?
In exam,
Because yeah, so for this we have to solve 3-degree polynomial for getting
yeah,
lambda
So
value.
see, this is just to give you a flavor for. Uh, I generally, whenever at least I can tell for my own situation, right? How I set QPs is I generally avoid too much computation. I hate computation. I like the algebra part, but I don't like root. The moment I see square root, it's like pisses me off, right? So you can expect little computation in terms of number crunching, right? So plugging things into calculator, all that will be as minimum as possible in quiz 2 and in term. So that much I can assure you. You
Sir,
won't have to do something very crazy like what we are doing here, right? So it will take 1 hour to just solve this polynomial, find the roots,
correct.
and yeah. So you don't have to worry about that. But you should know this, right? I just want you to know every step in the process, every step along the way, and see how it works.
Sir, like if you ask a matrix of 4 cross 4, it will not be possible for us.
Can you repeat it? I'm not able to hear you.
The matrix of 4 cross 4 or 3 cross 3, like what can we expect in exam?
Yeah. We will never give 4 cross 4 unless if we give 4 cross 4, there should be something absolutely simple about it or trivial that you can see right away. So only then we will give something like 4 cross 4.
Okay.
Okay. Okay. So we look at some properties of SVD before going to the final example. So recall that the SVD of A is U sigma V transpose. Okay. So there are several interesting properties. Property 1 is that you can express, or rather we use the person plural. So we can express A as the following sum of rank 1 matrices. Remember that I had mentioned this when we were discussing matrix multiplication. Someone asked me, where will we encounter rank 1 matrix at all? So this is where you will encounter rank 1 matrix. So you can express A as U sigma 1 U1 V1 transpose plus sigma 2 U2 V2 transpose, so on and so forth, plus all the way till sigma R UR VR transpose. Is a very, very important form of SVD. It's a beautiful representation actually, where, so I'll just add this so that it becomes clear. This is U1, okay, all the way till UM, okay, and B is likewise V1 all the way till Vn, okay. These are n columns, m columns, and D. So sigma. So yes, sigma is of course. I just call this diagonal of sigma 1 to sigma of minimum, right?
Yeah, I'm
Okay, so that is yeah. So you can now express A as the sum of rank 1 matrices. This is not very hard to see. Remember that this is sigma. So each sigma I or ui vi transpose is a rank 1 matrix, okay, meaning rank is 1, okay, as a sum of R rank 1 matrices where R equal to the rank of A. Okay, so is this clear? I'm not proving this, but this is not too hard to see from the decomposition. Does everyone get what is happening here? Anyone who's not able to see, not able to understand the statement, don't worry about the proof, but statement is clear, right? Yeah, so that's what I want. So property 2, in fact, many properties follow from this. The row space, 4 fundamental subspaces, of A are as follows. Okay, what are they? Row space, first the column space, and the
Null space.
null space and the
Row space.
row space,
Left space.
the left null space. Okay, can we directly obtain from these left and right singular vectors? Can be read off from the left and right singular vectors. Okay, so remember that there are m left singular vectors. So the column space is nothing but span of u1 all the way up till ur. And the first, so what does this mean? The first r left singular vectors span the column space. Okay, it's a basis, of course. So u1 to ur are linearly independent. They are orthonormal, therefore they are also linearly independent. Okay, you can also see directly that the rank is R. Okay, all this, they are all so closely tied together. This null space is the span of V R. So in fact, I will write row space and column space. Row space and which two are orthogonal? Column space is orthogonal to
Left
The
null.
left null space.
null space, right? So I'll write these two together. Okay, so remember that u1 to un is orthonormal. So ur plus 1 to u m, right, is the left null space. Okay, so remember also you have to remember that the column space is a subspace of Rm. Okay, so the columns are in Rm, right? So, and remember that this is in U, each one is in Um. So sorry, each one is in Rm. So this is the left null space. The last m minus r left, or rather the remaining singular vectors are m minus r, right? So the last m minus r left singular vectors span the left the space. Okay, the left null space is also a subspace of Rm. Okay, in fact, if you put these two together, there is something called a direct sum. Just like you have a union of sets, right? You have a union of subspaces. You can actually, this is outside the scope of the course, but there's a symbol for this. It's called what's the symbol called? It's a circle. Don't know what the symbol is. Exact LaTeX expression for that, but this is what it is. If you kind of add these two subspaces, you will get Rm, meaning the
Is it inner sum, sir?
sorry.
Inner sum? This circle inside addition.
What is that called?
Inner sum.
Inner sum. No, so yeah, but I want the. So this is a plus, right? So I want something which has a circle also. See O plus. Yeah. That this is called a direct sum. So don't worry about the exact notation. It's just that if you take any vector from this and any vector from this, you can get hold of all vectors in Rm. Okay. So so that is, these are two subspaces. Next one is row space. So the row space is nothing but what do you expect the row space to be? Span of
V1 up to VR.
V1 up to VR. Okay, and this is the first R right singular vectors is they span the row space of A. The row space is a subspace of
Rn.
N. Okay, the remaining thing is the null space. Null space is the span of what remains?
R plus 1 to Vn.
VR plus 1 to Vn. Okay, and the last n minus r right singular vectors span the null space. Okay, the null space is a subspace of Rn. Okay, you can likewise say that you add these two subspaces where this is a special notation V1 to VR and VR plus 1 to Vn, you can recover the original space Rn. Okay, so this is a very, very important property. This kind of summarizes everything you know about everything you would like to know about a matrix. Okay, so any questions here regarding the second property? Okay, so there's an
Sir,
outline. Right? Yeah.
Sir, if we know the basis for all the four subspaces, the vectors that which span the four subspaces, then we can say that we will get U and V for the singular value decomposition of A. We will not get sigma, but we can get U and V, right, sir?
Okay, so see not exactly because these are not any bases, right? So they are actually very specific vectors. They are not any vectors, right? So singular vectors. See, this is a consequence of SVD. Okay, can you go back from here to SVD? Not exactly. So what you're asking is, can you replace this by any basis for the column space and any basis for the left null space? Will you still get S? Can you still reconstruct U and V? Is that what you're asking? If I understood your
No,
question,
sir. No,
okay,
sir.
then,
I understood, sir, what you're trying to say.
okay, okay.
Those bases will have to be specific.
Yeah, yeah,
so
yeah.
that we D to
Correct.
hold.
Yeah. Okay, so the now link between A transpose A and A transpose, the left is U, right? So the left singular vectors are the eigenvectors of A transpose, and the okay, this is property. This is point number one. The right singular vectors are the eigenvectors of this. We already saw A transpose A, right? That is how we actually derived the SVD in the first place. Okay, and okay, this is point number two. The square of the singular values are what? Are the
Eigenvalues.
eigenvalues of A transpose A and A transpose. Okay, so this you have to take it with a pinch of salt. So these have different eigenvalues. This has n of them, this has m of them. But I hope you understand what we mean. Okay, or maybe just to be very clear, the square of the positive singular values. So all singular values or non-zero, right? What I mean is are the positive or non-zero eigenvalues of A transpose A and A transpose. Okay, these are once again two very important properties. Okay, is this clear to everyone? Okay, so this is these are three properties.
I have a small doubt.
Yeah.
Is sigma invertible?
That depends. No, sigma is first of all not necessarily square, right? So if it is so, but we will come to that. So that is what we will discuss finally when we discuss pseudo inverse. We'll come to that.
Okay.
Okay, here is a outline of the proof. I want you to for this span business, right? The row spaces. I want you to know this because this is a very, very useful form. This is this A equal to sigma 1 U1 V1 transpose plus dot 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 plus sigma R UR VR transpose, right? So it's a very useful form. Now, if you look at you consider A VI, what is it?
The sigma I UI.
We all see that. So one is we already started with this, but then you should be able to see it here also. So how can you see it here? So you AVI, AVI is nothing but this whole expression times VI. Okay, and this is like sigma 1 U1 V1 transpose VI plus sigma R UR VR transpose VI. What is VI transpose V something else? All these will go
So
to
0.
0, right? So you will be left with only sigma I UI VI transpose VI, which is 1. So this is just 1. Okay, so therefore AVI sigma I UI, you can see it this way. Now AV, so notice that since AV is sigma times,
Step, sir.
sorry?
So can you add that step VI transpose VI and then write this one? Because
Yeah.
Yeah, thank you.
Yeah. Yeah, so see, since AVI is sigma I UI, you should now be able to note that the span of, so AV is nothing but the set of all AV is the span of, it's the column space, right? So the column space is what? It involves use. So you must be able to see that from this equation. Okay. Also, we have this one. We also have this. Notice that A transpose. What can you say about A transpose? It will become
UI transpose VI.
It is VI UI transpose, right? So remember that this is a matrix. So it's like you swap the order and do transpose. So it will become V1 U1 transpose. Okay. So VR UR transpose. You have to, it's like two matrices, right? Two column. So one is a column vector. And you are multiplying that with a row vector. So the order changes. So this will become V1 U1 transpose. Is clear, right?
Yes, sir.
Yes, sir.
Okay. Now AUI by the same argument will be sigma I, A transpose UI will be
Sigma I VI.
sigma I VI. Okay. So please make note of these two. So is that the following are very important relations.
It's 10 o'clock.
Okay. Like yesterday, I'll just go till 10:30. Okay. So AVI is sigma I UI and A transpose UI is sigma I VI. Okay, at least this you can see for the first R positive singular values. It of course holds for all the way up to minimum of m comma n, all the singular values, but at least this much you must be able to see. Okay. Any questions in this? No? Okay. So if there are no questions, we'll look at one example and then two applications and close. Okay, so why did I add this example? Let me just give me 1 minute. Let me see why I added this.
Sir, because this is the only example which is not a square matrix.
Yeah, right. This is not square. So yeah, very important point is SVD is there for also rectangular matrices, right? So not just square. So in this case, if you are presented with a rectangular matrix like this, A is shape 3 cross 4, right? So since 3 is less than 4, it is easier to work with AA transpose. Okay. So you work with AA transpose to find the SVD. So step 1 is AA transpose. I'll just write it down. Okay, I have the AA transpose with me here. I complete this for you. So it's 420, 222, and this turns out to be 0, 2, 4. Okay, and if you compute, okay, so here is where you have to be careful. So what is step 2? Step 2 will be V, U, sigma. What will you compute?
V.
Yeah, it will be, no, will it be V? So A transpose A, it was V,
Sir, we'll calculate U.
U, right? So you have to be careful
Yes.
about this. So you have to be, if you do it for A transpose A, it is V, right? If you do it for A transpose, it is U, because this was this property, right? The left singular vectors, namely the columns of U, are the eigenvectors of A transpose. The right singular vectors, namely the columns of V, are the eigenvectors of A transpose A. So if you solve for eigenvectors of A transpose A, you will get V. But if you do it for A transpose, you will get U. So step 2 will
Okay.
assume U. Is this clear to everyone?
Yes, sir.
Okay.
Yes.
So what U turns out to be is, once again, I'll just this is just U is 1 by root 6. Uh, root 2, root 2, root 2. So this is the first eigenvector. So, and this is minus root 3, 0, 0. I'm sorry, we are not able, we don't have enough time to sit and solve this, because it's, what you can do is you can take this as an exercise. These are the correct answers because I'm copying this from a textbook, so it can't be wrong. So you can work it out at home later. Okay. Okay. So the singular values, therefore, you'll get the singular values as, what do you get? Let me see. What has he written? The prof. Okay. What will be the shape of this matrix? First of all, this is 3 cross 4. So what will be the shape of sigma?
3 cross 4.
This is also 3 cross 4. Okay. And since you have U, so the eigenvalues of U of A transpose are, I'll tell you that, 6, 4, and 0. Okay. So what will I fill here?
6.
6 or something else. Eigenvalues of A
Root
transpose are 6, 4, and 0. So the eigenvalues are
Root 6.
root 6, right? So square root of the singular eigenvalues. So root 6, 2, and
0.
0, right? So rest are all zeros. That's understood, but I'll just do this. Okay, so root 6, 2, 0. Is everyone clear why why we are filling it this way? So it's 6, 4, and 0. Therefore, root 6, 2, and 0. Okay, now this is another change from what we have done so far. Here there 4 steps. Step 1. Okay, yeah, correct. So V. Now we have to compute V. Okay, so we did AV equal to sigma U. So therefore, AV by sigma is U. Now U is what we have. So what equation will we use here?
A
U transpose UI.
Correct, right? So V, now V is what we want. VI is A transpose UI by sigma I for R. Okay, in this case, the rank is
3.
2, right?
3, sorry.
2, because you have
Yeah.
2 A transpose has 1 non-zero eigen, so 2 non-zero eigenvalues, right? So rank is 2. So you'll have, in this case, it will be 2. So you can get 2 of them right away. So they are, so just write it down. So V1 happens to be 1 by root 2. What will be the shape of the vector? So what will be the dimension?
The 4 cross 1.
4 cross 1. Okay, so 4 cross 1. This is 0, 1, 1, 0. V2, you, it seems, is according to the prof, it is minus 1, 0, 0, 1. Okay, again, once again, minus 1, 0, 0, 1. Okay, so you need how many more vectors to complete V?
1 more.
Sir, 2 more. I think.
2 more.
2 more, right? So because this is 4 cross 4, right? This is
Yes.
okay. Okay, so I'll add this root 2 outside. Root 2 is outside. This is 0, 1, 1, 0. So here it's easy for you to eyeball and tell me. Can you tell me two vectors which will be orthonormal to this, orthogonal to these two? One you can tell me to begin with.
0, 1, minus 1, 0.
0, 1, minus 1, 0. So is this ortho? Yeah, this is orthogonal to this. Yeah, good. Okay. What is one more?
1, 0, 0, 1.
0, 0.
Minus
Minus
Exactly.
1.
Minus 1 is it? This one is minus 1. This is
1.
this has to be 1, right?
Yeah.
Correct? Yeah. Okay, good. Yeah, so that is correct. So 0, 1, minus 1, 0, 0, 1, 0, 0, 1. Okay, so that is V. So in this case, V is easy. Usually you can expect things like this. So it won't be too hard to
It
compute.
will be minus 1, right?
Sorry?
Minus 1, column C4, last element.
1 only, right? Because if you multiply 1 and 1, minus 1 and 1, it is 0. So
Okay, I'm checking the wrong column.
okay, is it clear to everyone how we got V in this case? By eyeballing, we can get V3 and V4. Okay. Any questions in this example? If not, we'll go to the applications. Okay. We'll first finish this quickly. So the pseudo inverse, the pseudo inverse is a matrix. So if A is a matrix of shape m cross n, then its pseudo inverse is a matrix of shape n cross m that has inverse like properties. Okay, it's not exactly an inverse, that's why it's called pseudo. Pseudo means fake so far, somewhat, right? So it's a fake inverse, or you call it, so it's pseudosines, likewise pseudo inverse. The inverse like properties. So and is computed using the SVD. Okay, the nice part is that it exists for every matrix, not just invertible matrices, obviously, and it is equal to the inverse for invertible matrices, right? So that is the nice part about it. So how is the pseudo inverse? So you usually represent it as a dagger. Okay, this is called a dagger. Instead of A inverse, it's a dagger. So it is nothing but once you have SVD of A, so if the SVD of A is sorry, SVD of A is like this, right? So from property 1, then the pseudo inverse is often called the Moore-Penrose. Okay, so I don't know about Moore, but Penrose is a British mathematician. So some of you might be knowing Penrose. So he's famous for some theorems in physics, actually mathematical physics concerning black holes. So those of you who are black hole astronomy, cosmology freaks, you can go and look up Penrose. So what is the pseudo inverse? It's actually 1 by sigma 1 V1 U1 transpose plus 1 by sigma r. So this is out of scope of the syllabus, right? So don't worry if you don't memorize this or remember this. Okay, so this is the pseudo inverse, which has inverse like properties. Okay, so where is this used? If you have a system of equations, Ax equal to b. Remember, right? This is what we started off the course with in week 3, the linear algebra part. Okay, the least square solution to Ax equal to b. So Ax equal to b may have a solution, it may not have a solution, but it will always have a least square solution, right? We have established this. A transpose AX equal to A transpose B. If you solve that, okay, so that is given by, it's a very nice formula, A dagger B. That is all. Okay, so remember that this was what we called as X hat. So if you want to find out the least square solution of a system, you don't need to solve all that A transpose A inverse A transpose B, all that. All that you need to do is find the SVD of A and find the pseudo inverse. Pseudo inverse is very simple. Once you have the SVD, you just need to invert the positive singular values V1 U1 transpose, and you have the least square solution. Multiply that with B, you have the least square solution. Okay, in fact, it is the, it has a, it's the least norm. In fact, I leave that. Okay, so it's too much for now. But all those who are doing MLT together, you will be seeing this in week 6 and 7, week 1 and week 2 also, where you will be using pseudo inverse quite a lot. The pseudo inverse comes from SVD. Okay, there's a particular pseudo inverse called the Moore-Penrose pseudo inverse. Okay, is this clear? So you don't need to really know this, but it's good knowing this. SVD has its uses. Okay, one final example application. So if the SVD of A is okay, then we can approximate A with the help of a matrix with a lower rank. Okay, this is a very popular application in machine learning. This is used in many places. Some of the places where it is used, so it's used in recommendation engines to simplify data matrix. Okay, it's used in image compression. It's one way of understanding PCA, which we'll be doing next week. Okay, which is dimensionality reduction. You remember week 1 is what we started off with, right? So this is one of the, okay, so what does this mean? So if I'll just state this, so the best matrix of rank K, what I haven't defined what best is, it's not needed now, that approximates A is given by the following, right? So you take SVD of A, you only retain the top K singular values and throw away the rest. Okay, so then this is A hat. Okay, then A hat is an approximation of A. It is best in some sense. Okay, so it is best in what sense? A, so A is as close to A, the original matrix, as possible, meaning the approximation error is very low. Okay, so I know that I have not given you enough information here, but this is just to get you a sense of where SVD is used. So I'll just demonstrate one example of this low rank approximation for an image. Okay, so immediate application is image compression, meaning do you all know how images are represented in a computer?
Matrices.
Yeah, so every image is a matrix, right? So every image is a matrix. Okay, so for example, an image could be 1000 cross 1000 matrix. Okay, so each value in each cell, it is called a pixel. Okay, so these pixels usually range from 0 to 255. Okay, so this is I'm giving you an example of what is called a grayscale image, meaning a black and white image. So a black and white image is just a matrix. Okay, So it's just a matrix. So if you want to represent a matrix, if you want to represent an image using a system computer, you have to present it in the form of a matrix, and that is like 1000 cross 1000. Okay. So why is this a big deal? So one problem is how much space will this occupy? Okay, so this is a question. So if you have 1000 cross 1000, you have 10 power how many pixels?
6.
10 power 6 pixels. Okay, so each pixel is going to occupy certain number of bytes. Okay, occupies, say, so 255. Each value ranges from, so you could say that there are 4 bytes. Let's say 4 bytes. So it's like 4 into 10 power 6 bytes. I don't know how many. What is that? 4,000 bytes is 1 kilobyte. Is that correct? Roughly. So 4 into 10 power 6 will be 4 MB. Is that correct? Is that calculation correct? See, 4,000 bytes is 1 kilobyte, right? Roughly. Yes or no?
1000 bytes is 1 kilobyte, right?
Sorry,
Yes, sir.
is 4 kilobytes, right?
Yes.
Yes.
So 4 million, that's what this is, right? So 4 into 10 power 6 will be roughly 4 megabytes. Is that correct?
Yes.
Okay, roughly. So I'm just giving you very rough estimates. So the question is, do we need to represent this, store this image as 4 megabytes, or is there a way of using fewer values and still storing the image? Okay, so that is what I wanted to tell you. So yeah, someone who is not on, please. Yeah, so I'll just share one experiment where I've already done the SVD for an image. Okay, so are you able to see the screen now? I've changed the screen.
Yes, sir.
Okay, so this is an image. Okay, this is image of Mr. Einstein. So 11,004 cross 903 pixels are there. This is a matrix. So if you look at this matrix, there are 1,100 rows and 900 columns approximately. So each pixel here, you are not able to see the pixels because there are 1 million of them roughly. But then everything is a value between 0 and 255. Okay. So instead of representing the image as 1 million pixels, what you can do is you can first find the SVD of this matrix. Okay. So if you find the SVD of the matrix, so first of all, it's rank 903. So you can compute the rank actually. So it's, in this case, it's full row rank or column rank? Column rank, right? So in this case, the column rank is 903, it's full rank. Okay. So it is full rank, but actually speaking, you don't need the full rank matrix to store the image. You can actually settle for something of a lower rank. So what we have here is, I've plotted the singular values. So I'll just hide the code and only show you the result. So this is singular values plotted against the x-axis. X-axis is the number of singular values. So there are 903 of them. Okay, remember that singular values is minimum of m comma n. Okay, so there will be 903 singular values. In this case, this is a log scale. So y-axis, it starts with 10 power 5. So what is happening is the first 20 or so singular values capture most of the information in the matrix. That's how we say this. Okay. So the higher the singular values, more is the information content captured by that part of the matrix. Okay. So the first 20 singular values are kind of capturing most of the information in the matrix. Rest of them, if you see, it's it's a precipitous drop. Okay, from there.
So what is the y-axis of this graph?
Y-axis is the singular value. Okay, the first singular. So in descending order, so 10 power 5
The
is
highest singular value, sir. Is
yeah,
that what it is?
yeah. X-axis is like, this is the 200 singular value. 200 singular value is maybe something like between 10 square and 10 cube. So 100 and 1000, it's something there. Okay, so
Got it,
903
sir. Yes.
it will be something. So what do you do? So you use the SVD, and this is what you do. These are the approximations that I was talking about. So if you, this is a rank 1 approximation. Do you see why this is a rank 1 approximation?
So because every column is a multiple of the other.
Exactly. Every column or every row is a multiple of the other. You can see the pattern here, right? You see that there are horizontal strips of varying intensity or vertical strips of varying intensity, but they are all strips. I hope you are able to see that. So the columns are, there is only one linearly independent column. This is a rank 5 approximation. So rank 10, right? If you retain the 10 singular values vectors alone, you are already able to see, make out a face, hair, shirt, all that, right? If you go to 20 singular values, you get a pretty decent approximation. 100 is almost the same as the original.
So this
Okay.
is the first 100, right, sir?
Just yeah, first 100. So that would be like somewhere here. Okay. So the first 100 is capturing most of the information content in the matrix, and this is what allows you to compress the matrix. Okay. So remember that the actual matrix will require you to write down sigma 1 u1 v1 transpose till sigma 903 u3 v3 u903 v903 transpose. Instead, what you're doing is you're truncating it after 100. Okay, but still you are able to retain the information content in the matrix. So this is one of the uses of singular value decomposition. Okay, so I hope the example was somewhat clear. So in this case, A hat will be whatever image I showed you, right? A hat is actually just 100. It stops with 100, whereas the full A will be going all the way till 903,
903.
right? So because that's the rank. Okay, so where is the saving coming from? You are saving, the saving is coming from the fact that you don't need to save 903 minus 100, right? So about 800, the information in that part of the matrix, you don't need to save at all. So you only need to save these three objects. So the 100 singular values, the 100 right singular vectors, 100 left singular vectors, and that if you actually work it out, it will be a good reduction in storage. Okay, while not disturbing the quality of the image too much.
But
Okay.
sir, we will have to calculate, first of all, calculate all of them, all 900 of them, and then choose, right, sir?
Correct. Yeah. So that computational burden is there, but it's one time, right? If you are if your intent
Yes,
is
sir, one time.
yeah. So that is there.
Sir,
Yeah.
so out of 903, we only select 100 and 800. We suppose discard. Suppose we want to create the original image quality. Will it be possible because 800 informations are lost for us?
You whatever I showed you, right? So see, visually you are able to reconstruct something close to the original, but if you want to like exactly have the original, right, then you need all the 903. So there is no way you can, there is some loss. So this is an example of what is called a lossy compression. So it's not a lossless compression. You are going to lose some information. That's a trade-off, right? So the trade-off is how much memory do you want to save, and how much error in approximation are you willing to tolerate. So the smaller the memory footprint, bigger the error.
Okay.
Okay. Yeah. So that's all I had for today. Any other questions on SVD? not, we'll stop here because there's nothing else that I can think of. Just to be, yeah. So these are the.
This loss calculation also, sir, like we are supposed to do like how much loss will be there.
Loss. Yeah. So if you want to compute the loss, right? Though the loss is actually nothing but, I haven't introduced that, but it's the. So for example, if A is your matrix, right, and A hat is your approximation, there is something called a matrix norm. So the loss in approximation is given by the matrix norm. This actually turns out to be the k+1 singular value. Okay, so this is called, if you're interested, you can go and refer to what is called the spectral norm or operator norm. Okay, so these are norms for matrices. So you can give the error in terms of this norm. So just as you have norms for vectors, right? So the norm of a vector is norm of v is what? Length of the vector. Likewise, you can define the length of a matrix in some sense, or the size of the matrix. So that is very closely associated with the singular values. So that is actually another application, matrix norms.
Okay.
But yeah.
The reason, sir, I asked this question because I participated in one of the hackathon that was organized by ISRO, and there
Okay.
the project I took was the images that ISRO provided us of the clouds. We were supposed to clean that image, and then we were supposed to calculate the loss. We have to reconstruct that image, and whatever the loss was there, we have to minimize that loss. So it was like whatever we are learning over here, same thing. It was there also.
Oh, nice. Okay. Okay.
I could relate whatever you are explaining over here. So.
Right. Yeah.
Thank you, sir. It was a useful explanation.
Yeah. Thanks. So any other questions regarding SVD or whatever we did today? Any part of the session? Okay. Yeah. If not, we'll meet again. So Saturday there will be a general doubt clearing session, and next week we'll start PCA. Okay. Yeah. Thanks everyone.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.